The derivative mode is used in only about 10% of the loops. However, the importance of derivative is more than this might imply. A common application of derivative is in slow temperature loops in reacting systems. These are among the most important loops in a plant. When originally introduced, the derivative mode was called preact. This suggests that derivative is anticipating the process and taking control action in advance. In some circles, the term lead is also associated with derivative. Consider the trend in the illustration. The process variable is below the set point, but moving toward the set point. At a point in time, two items of information are available for the PV. Its current value, its rate of change, or dPV dt. Issues arise in computing dPV dt, but these will be deferred to a subsequent video. Projecting the current rate of change provides the basis for a simple predictor for future values of the PV. Projecting the PV one derivative time into the future gives the projected value C hat. C hat equals PV plus the derivative time T sub D dPV dt. In the illustration, the value of C hat is closer to the set point than the current value of the PV. However, this assumes a reasonable value for the derivative time. The control error E is the difference between set point and PV. The projected control error E hat is the difference between the set point and the projected value C hat for the PV. For a given value of the control error E, a PI controller would take a certain control action regardless of the rate of change of the PV. But if the PV is moving toward the set point, as in the illustration, it seems logical that the controller should be less aggressive. Conversely, if the PV is moving away from the set point, it seems logical that the control error should be more aggressive. In the control equation for the proportional mode, suppose we replace the control error E by the projected control error E hat. For the example in the illustration, the PV is moving toward the set point. The projected control error E hat is less than the current error E. Basing the control actions on the projected control error makes the controller less aggressive. Suppose the PV is moving away from the set point. The projected control error E hat would be greater than the control error E. Basing the control actions on the projected control error E hat makes the controller more aggressive. The value of the derivative time tells the controller how far into the future to project the current rate of change. The terms long and short are also associated with the derivative time. But unlike the reset time, the contribution of the derivative mode increases with the derivative time. If the value of T sub D is too short, the full potential of the derivative mode is not realized. If the value of T sub D is too long, the errors in the projected value C hat are excessive, leading to cycling and possibly instabilities in the loop. Let's express the projected control error E hat in terms of E and PV hat. For a reverse acting controller, E hat is set point minus C hat. Replace C hat by its expression in terms of PV. PV plus T sub D dPV dt. Set point minus PV is the control error E. The projected control error E hat is the current control error E minus T sub D dPV dt. For a direct acting controller, the sign on the derivative term is positive. Using this relationship, let's add derivative to a proportional only controller. Write the proportional plus bias control equation with E hat instead of E. Now replace E hat by the relationship just derived. Controller output M is controller gain K sub C times control error E minus T sub D dPV dt plus the controller output bias. This controller has a proportional term and a derivative term, and is commonly called a proportional derivative or PD controller. Like proportional only, the PD controller exhibits offset or droop, hence its infrequent use. Doing the same to the PI control equation gives a PID control equation. Start with the PI control equation, written in its customary form, but with E hat instead of E in the proportional term. Replace E hat by E minus T sub D dPV dt. Then write the terms in the order suggested by the PID. E is the proportional term, integral of E dt is the integral term, and dPV dt is the derivative term. For a direct acting controller, the sign on the derivative term is positive. This equation incorporates proportional, integral, and derivative. The proportional integral terms are based on the control error E. The derivative term is based on the PV. We will demonstrate the effect of derivative using the hot air temperature controller for the hot air furnace. Initially, the controller is PI. The controller gain is 1% to percent. The reset time is 1.5 minutes. Derivative time is 0. As a point of reference, we first obtain the response for PI control. Switch the controller to auto. Then change the set point from 210 to 220 degrees Celsius. When the PV attains the set point, change the derivative time to 0.2 minutes. Then return the set point to 210 degrees Celsius. When the PV attains a set point, place the simulator in hold. With derivative, the oscillations decay more rapidly. Although sometimes used, let's avoid the expression more stable. A loop is either stable or it's not. A loop whose oscillations grow rather than decay is unstable. A loop whose oscillations decay is stable. Both of these responses are stable. At the line in the sand distinguishing stable loops from unstable loops, The oscillations neither grow nor decay. How near a loop is to the line in the sand can be thought of as the loop's stability margin, or margin of stability. The more rapidly the oscillations decay, the greater the margin of stability. For a large margin of stability, no oscillations are present. Our example illustrates the ability of derivative to cause oscillations to decay more rapidly. Pi versus PID. The direct effect of derivative is to increase the margin of stability. As implemented in most commercial control systems, the derivative is based on the PV, but the PID equation in most control text is expressed entirely in terms of the control error E. Some, but not all, control systems provide this option. This is the subject of the next video.